rejects the common mode signal. So we know that difference amplifier or differential amplifier is represented by schematic like this. Where R2 and R1 are the gain setting resistor. We have input voltage VI1, VI2 applied to the two input of the operational amplifier. And these are some extra resistors that we have here. And that is how the configuration of differential amplifier is. And at this node, we have output voltage. So what do we mean by a common mode signal? Common mode signal is a signal that has the same magnitude, and let's say it could be a noise, and that is applied to both of these terminals of the operational amplifier at the same time. So the difference between them is 0. So they are of the same magnitude. Okay, so how we can represent that signal? We say that in another schematic we draw here. Let us see. So this is a differential amplifier. It will amplify the difference that appears at these two terminals. This is V1 and this is V2. And the difference between these two terminals will get amplified. That is the job of differential amplifier. But what about the common mode amplifier? So we see here, we short these two signals and we apply another signal called as VCM, which is VCM is common mode signal. And that's how it is. So again, we apply the same analysis. Amplifier has a finite gain in the closed loop indicated by A. The potential or voltage at this terminal is V2, at this terminal is V1, and the difference between these two terminals is indicated by VID, and VID is nothing but magnitude of V1 minus V2. So we can also write as V2 minus V1. Okay. So how to get the output voltage for this kind of circuit configuration? So we know that we can apply the superposition theorem. To this circuit, where the output would be V01 plus V02, where V01 is the output of the circuit when we have only voltage applied at this negative terminal active, and the voltage applied at the positive terminal is disabled. And VO2 is the output of the amplifier when the voltage at the positive terminal of the op-amp is active and the voltage at the negative terminal of the operational amplifier is disabled. But in this circuit configuration, we don't have such case because both of these inputs are shorted and a single input called as, that's why we call it as a common signal is applied to this terminal. Okay, so how do we analyze this circuit? So we don't have the superposition right over here. We cannot apply that. Instead, superposition is applied to this circuit configuration as we see here. Okay, and we've derived the gain of this circuit, which is given by R2 over R1 VID. VO is equal to, okay, and AD, which is the ratio of these two signals, output over input. That is how the expression for this configuration. And now we are about to derive the output expression for this circuitry right over here. So how we do that? We first calculate the voltage at this node, that is V2. So let's see what V2 is. So V2 can be calculated. We'll apply the voltage division rule here, which is R4 divided by R4 over R3 multiplied by VCM. Okay, so that's how we have this voltage. And this voltage, because of the virtual ground concept, we know that because we assume that the gain is infinite, so this terminal essentially is shorted to this terminal. V2 is shorted to V1. Okay, that's the assumption. That's why V2 becomes equal to V1. And once we know that the output, which is the expression that we have derived here, which is R2 over R1, V2 minus V1. Okay, so we just have to plug in the values of V2 and V1. We know that VCM minus V1. So V1 and V2 are the same. Therefore we can say that output voltage is nothing but R2 over R1 times 0. Therefore, it is 0 volt. So ideally, this is how we have the output for the common mode input. Okay, so any signal that is common to both of these terminals will get summarily rejected by the differential amplifier action. That's the advantage of this circuitry, right? So AD is the differential gain. We have seen that, which is the ratio of output by VID, and it is set by the ratio of the resistor. ACM is the common mode gain. And it is again the ratio of output voltage divided by the input voltage, and it is 0 ideally, actually. Okay, but some voltage would be there if we have a mismatch between the values of these resistors right over here. We can see that then we can have, or there is a difference voltage between V1 and V2, that difference will get amplified. Even we have these common signal applied to over here, and that will give the value of these output in that case won't exactly be 0, and therefore ACM will have some magnitude right over here. So we define another term, that is CMRR. Okay. It is called as common mode rejection ratio. And it is the ratio of differential gain divided by common mode gain. So we know that R2 over R1 divided by 0, and it has to be ideal value of it is infinite. In dB, we can take the magnitude of the gain, which is AD over ACM. So that's how we get the CMRR right over here. Okay. So we continue with this extension of this circuit, and we come back to instrumentation amplifier we've seen before. It has 3 amplifiers, A1, A2, and A3 right over here. How to analyze this circuit for the differential gain as well as for the common mode gain. So we know that ideally we want differential gain to be as high as possible and the common mode gain to be as low as possible. Ideally, we would like to have a common mode gain to be 0. We don't want any signals, for example, noise, to affect the operation of the circuit. We don't want any gain for the common mode signal. So let us analyze this circuit. So we know that that's the voltage at V2, and here we have V1 is equal to Vi1. And because of the virtual short, this voltage comes over here at this node. Okay, so the voltage at this node is Vi1. Similarly, for the virtual short concept, the voltage at this node right over here is Vi2. Okay, so we are analyzing it for the differential circuit. So the current through this resistor is simply the voltage drop across this resistor, which we say that I is Vi2 divided by R2. The current through this resistor, that is right over here, that goes to ground, and this current goes to ground also. That is, we say that I is equal to Vi1, that is the drop across this resistor, voltage drop across this resistor R1. All right, so we can say that the current through this resistor is nothing but, what is the voltage that comes here? Let's say voltage over here VO1, that is the output voltage of this amplifier A1. Voltage here, let's say it's a VO2, that is the output voltage of this amplifier. So if we closely observe this circuit, what we see here, they are essentially two independent non-inverting amplifiers. So they are acting as a buffer with a voltage gain, with a gain. Okay. So we see here for this case, right here. So that's the voltage follower 1, a voltage follower 2. So the advantage here is that we have a gain that is set by, this is actually a resistor R1. Okay. So VO1 is 1 plus R2 over R1 times Vi1. So it's simply a non-inverting amplifiers. 1 plus R2 over R1. V0 is Vi2. Okay, so we were talking about the current through this resistor R2, which is differential difference across the two terminals of this resistor divided by the value of it. Okay, so it is current through R2 can be written as Vi1 minus VO1. Okay, and current through this resistor R2 can also be called as, defined as like this. It would be V02 minus Vi2. And we can write the value of VO1 and VO2. Okay, and we see here this current that passes through this, and voltage here is V2 for this amplifier 3. Voltage here is V1, and we assume the gain of this amplifier in open loop ideal gain is infinite. Therefore, we can short these two terminals. We assume that they are shorted. That's the concept of virtual ground. And this current then comes back through this loop, and that's the current that is passing through it. Okay, and goes back to the ground. So how we actually see this? So this is the third part of the circuitry that we see here. Okay, so that's our differential amplifier. And how we analyze that circuit is right over here. We can simply say that this differential amplifier, that is amplifier 3, has this configuration where we have resistor R4, this is the resistor R3, and the voltages that appears across the two terminal, at its two terminal, they are V01 and V02, which are the output voltages of these two amplifiers. That becomes the input of this third amplifier. Okay, so we know that this VO1 has the value of 1 plus R2 over R1. Right here, VO1, 1 plus R2 over R1 times VI1, and V02 is equal to 1 plus R2 over R1 VI2. That is how we have this circuit built. And we know that the final gain of this amplifier is set by the ratio of R3 over R1 and additional gain that comes because of these first two amplifiers. That is how the final gain of this amplifier is. We have seen this in the previous module. Okay, so that's how the differential gain will get calculated right here. But we can solve this expression also. Let us solve this to see how it produces this differential gain of this value. So what we see here, we output of this differential amplifier, we apply the superposition here. We apply the superposition here. So what we do here, what we understand, the output voltage V0 would be given as V001 plus V002. So V001, let's say, is the output of the difference amplifier when V01 is active alone. So it means only this voltage source is active and this is terminated to the ground. We disable this input. And V002 is the output of the difference amplifier when V02 is active alone. What it means is that we make VO2 active in the second case and we disable V01 by terminating it to the ground. So in that case, we can just apply the superposition and get the expressions for V01. That comes out to be minus R4 over R3, 1 plus R2 over R1, VI1. And this second output comes out to be V2. And the V2 is the potential right over here. Okay, so we see that. We can solve this. So value of V2 is this factor actually. And final voltage can be written in this form. If we continue solving it, we have this value finally in hand. Vi2 minus Vi1, which is the difference voltage finally. And this takes the final form 1 plus R2 over R1. So we see that we have a multiplication of the two gains. This first gain is because of the amplifiers A1 and A2, and the third, this gain is because of the amplifier A3 into VID. That is the difference between the two voltages. And we can write that differential gain is V0 by VID, which is the multiplication of the two gains. Okay. What about the common mode gain? Which is ACM. You see that the common mode gain should ideally be 0. So let us try to analyze this circuit for the common mode circuitry. So what we see here, let's say Vi1 is not going to be, what I mean here is that this Vi1 and Vi2 are shorted and a common signal is applied to this signal called as VCM. So what happens when we have VCM, the voltage that comes here is VCM. The voltage, because of the virtual ground, voltage that comes here is also VCM. Right? And of course, the currents are then this Vi1 and Vi2, they all become VCM. So instead, the final output of these VO1 and VO2, instead of Vi1 and Vi2, we can write VCM right over here. This is VCM and that is VCM. So what is to be noted, this common mode signal is getting amplified by the amplifiers A1 and A2 by the same gain factor, 1 plus R2 over R1, which is similar to the case as if the difference between the two signals Vi1 and Vi2 is applied to these amplifiers. So essentially, this first two stages, A1 and A2, they are amplifying the common mode signals by the same gain, magnitude of the gain. So these signals get transferred to the third stage, that is A3. So the differential amplifier has the job of rejecting the difference between these two signals, right? So since the VCM have the same magnitude, so final output, we can see. So output in the case of common mode signal is again this way. VCM minus VCM, because that's how the Vi2 and Vi1 got replaced with. So we know that this factor goes, this term is 0, so therefore output for the common mode signal is 0. But we know that if there is a mismatch between these two values, there is a difference created right here. So the VO gets appeared in the output. So this is a problem with the instrumentation amplifier. And to solve this problem, we have another configuration where we make some changes. And we have seen that. So this is a modified version of the instrumentation amplifier, IA. So what we see here, if we take a look at the previous diagram, we have these two resistors, R1, and the terminals, one of the terminals of both of these resistors is connected to the ground, and other terminals are connected to the respective operational layer. So what we do is that we remove the ground, and two resistors, they are replaced by a single resistor in this configuration right over here. So now this resistor becomes 2 times R1. So we again apply the concept due to virtual short. This potential comes right over here, that is Vi1. Because of the virtual short, this potential comes here, VI2. All right. And then the current flowing through these resistor, that is I, is nothing but VID, which is the difference between the two voltages divided by the value of this resistor. Okay. So it is nothing but VI2 minus VI1 divided by twice R. This current is passing through this resistor right over here. And then we know that because of the virtual short concept right over here, this current comes back and passes through this resistor. Okay, so the current through this resistor is again VID over R2. Current passing through this resistor is VID over R2. Not really R2, is the same current actually. This is VID over 2R1 and VID over 2R1. Okay, or we can also say that the current that will pass through these resistors will be the drop across this resistor, the voltage drop, which is, let's say these are the two output voltages. We've seen that in the previous case. So that is the VI1 minus VO1 divided by the value of these two resistors, R2. And this is again VO2 minus VI2 divided by the value of this resistor. Okay, we can also have that kind of representation for the current. So how to analyze this circuit for the differential gain? So what we write here is the expression, let's say VI1 minus I times R2, that is this voltage over here, minus the drop across this resistor, minus that equals to V01. This is the output voltage. Okay, so V01 is VI1 minus VID 2R1. That is the current multiplied by the resistor. Similarly, we can have the value for V02, that equals to VI2 plus I times R2. We know that this is the drop across this resistor, voltage drop across this resistor, plus this voltage is the V02. Therefore, V02 is VI2 plus the value of the current is VID by 2R1 multiplied by R2. Okay, so we have, once we know the value of V01 and VI2, these two output voltages of operational amplifier A1 and A2 are the input to the third amplifier. Okay, so and the output of the third amplifier is given as V001 plus V002 because it's a differential amplifier. So V001 is the output of this A3 when only voltage at this node, which is V01, is active alone, where this is disabled, voltage at this node is disabled, and V002 is the output of A3 when only the voltage at this node, which is V02, is active alone, and voltage at this node is disabled, which is VO1 is connected to the ground. Okay, and these are these two voltages that appears at these two terminals. So let us analyze and solve this for this. So V001 comes out to be minus R4 over R3 VI1 minus VID times R2 divided by 2R1. That further gets simplified into VI1 2 times R1 minus VID R2 divided by 2R1. So we have this expression for the V0 and V0 can also be solved. V2 times 1 plus R4 over R3. V2 is the voltage at this terminal. This is the voltage at V2 and this is the voltage V1. So we have these two values. So finally, V0 is V0 plus V0 If we put in these two values and we simplify further, we get these values right over here. So let's say we try to put in the values of both of these values. Is minus actually plus R3 solve it, and finally what we have here is R4 over R3 VID. Okay. So that's all. We have this amplifier.